Okay. Okay. Can you see my screen?
Yes.
Okay. Good morning, everybody. And today I will present the issues on the millimeter wave scheduling and also the challenge. And this is my outline for this presentation. First is the related resource, the study resource that I already studied before. And then the other issues and challenge that I found uh, after uh, after studying the resources. And related resource, there are two papers that I study. First is the evaluation of scheduling algorithm for 5G mobile system. Wait a minute. This one, and this one raised the issues of fairness. And then the second one is the resource allocation for millimeter wave MIMO system. And this one raised the interference issues, which is related also to the QoS requirement. First one, we will discuss about the fairness issues. So there are several algorithm that is talked and discussed in this paper. So I will describe this scheduler. First one is the maximum rate scheduler. So actually, this model is a simulation model. So there is an environment model that accept a packets and it will spit out and get out the channel quality indicator. And the channel quality indicators will be used by the scheduling models to decide which packet need to be sent to the user. So the maximum rate scheduler aim to get the maximum throughput of the network, but uh, it doesn't guarantees all of the UE will get the same quality of service. And this led to a starvation for the UEs with low channel quality indicator because the maximum rate scheduler will prioritize packets with the best channel quality indicator. So the user with the best quality will get served first in this scheduling model. So that the network will get the most throughput from it. And then the second scheduling algorithm is the round robin scheduler. So the round robin scheduler basically just send a packet from one user to the another users one by one. So this scheduler guarantees service for all users. However, it doesn't aware of the channel condition. So it doesn't know if the user UE1 has uh, the best quality or UE63 which doesn't have a good quality. All of them has the same uh, priority in this round robin scheduler. And the next one is the proportional fair scheduler. So in this proportional fair scheduler, the scheduler tries to give a fair scheduling algorithm and scheduling resources to the UE. So the UE that has the best channel quality indicator, the CQI0, will get 3 packets sent at each round. And the CQI1 will get 2 packets from each round, and CQI2 and 3 will get 1 packet in each round. In this way, every user will have chance to get the packets, but it is proportional to the channel condition. The best channel, the best quality will get most of it, and the other one will get slightly lower packet delivery. And then the last one is the proposed by the paper. So it is a UE-based maximum rate scheduler. So basically, each resource block is divided for 4 channel quality indicator. So CQI1 will use resource block 1, CQI2 will use resource block 2 and 3, and the following is the same. And so the packet will always be forwarded, and in each of the resource block, there will be some kind of level that is named QoS, QoS class indicator. So for each QoS class indicator, the packet will be similar to the proportional fair scheduler. So the first one will get 4 packets sent, 3, 2, and 1. That's it. So for the analysis, as we can see here, for the simulation steps, for the throughput result, the round robin and maximum rate get the most of the throughput, but the proportional fair and UE based maximum rate will get slightly lower because it considers the channel quality indicator while the round robin does not. And this is the throughput for per resource block. As we can see here, the resource block 1, which is the best channel quality, will get the most packet delivery for the proportional file and UE based maximum rate. However, for the maximum rate and round robin, it will all have the same level of service because it doesn't consider the channel quality indicator. This is the total packet sent per UE for each group. So this is the group 1, group 2, group 3, and group 4. All of the total packet is considering the different channel quality except for the round robin, which has the same number of packets regardless of the group. And the last one is the measurement of the fairness. As we can see here, there is a requested packet percentage for the user group 1, user group 2, user group 3, and user group 4. Each one has different packets that is requested. And as we can see here, the round robin has the same level of fair of delivery, that is 25%. And this is not fair because the user group 3 has the most packet requested, but only served by 25%. And the other 3 algorithm get the most, has the most fairness level compared to the round robin. However, the maximum rate will not serve the same level of fairness on higher traffic. I'm not sure why the authors did not try on the higher traffic, only try for the 64 amount of UE. So that's for the fairness issue. So we need to balance speed with the QoS and throughput of the network. The next one is related to the beamforming, that is the interference issues of the millimeter wave in a MIMO system. So for the background, as already mentioned by Jojo and Dennis before, beamformings enable us to utilize one more resources, the spatial resource. As we already know that the LTE and 5G, we utilize the time resource and also the frequency resource. And with the beamforming, we have one more resources, that is the spatial resources. With the additional resources, there is a need for a resilient and good scheduler to deliver the best services we can for the user. But the problem is, with the new capability of directed beam, it introduced a new interference type, that is the inter-users interference in the main lobe and also the side lobe. As we can see here, the user one get an interference on the main lobe from the user 2, and also get the side lobe interference from user 3 and user 4. That is the main issues of the beamforming, and that is discussed in this paper. So next I will talk about the system model that is used to evaluate this interference. So let a base station have a K amount of users, M amount of subband resources that will be allocated, and N amount of beamformer. So beamformer is the antenna that is trying to transmit different beam from each other. And this is the assumption that is used by this model. So the base station and mobile station will have the same beam width for the synchronization with the width of theta. And due to the high path loss of millimeter wave, the intercell interference will be negligible and will not be discussed in this model. And then the beam gain for the transmitter and receiver, and the receivers would be the same. This is the formula that is used to calculate the beam gain. This is the gain for the main lobe for the transmitter and receivers. That is the same for the assumption. And this is the gain for the side lobe for the transmitter and receivers. And the value of epsilon here is less far less than 1, it is the beam gain value for the side lobe. So the next one is the SINR formula that is used to calculate and evaluate this model. So this one, and I will try to explain it. So this is the SINR of user K. So as I mentioned before, there is K number of users, and in the subband M, because there is M number of subband, and also a number of beam that that can be produced by the beamformer. So there will be a lot of SINR for each user by band and also by the beam. This one is the transmitting power, and then this one is the beam gain for the transmitter and receiver. So this is the signal power part, and then this one is the channel gain, and this is the path loss decay. And then for the interference part, this is the interference part. It is not the same with while J is not the same with N and I is not the same with K, because we measure the interference for the user K that is sent by the beam N. So it's not the same beam, but the same subband can also uh, hinder or make an interference with the main beam. This is the power transmitting for the other beam. This is the channel gain, and then this is the path loss, and this is the beam gain for the both main lobe and the side lobe. And then the last one is the additive white Gaussian noise, so the interference and the noise. This will be used to evaluate the model. So what do the proposed solution here? So the author proposed a main lobe interference avoidance, or MIA algorithm. So how does it work? So actually this is the evaluation steps. So first it is initialize the scheduling matrix, and for its sector or its location, assign its user with available subband. So if the subband is not enough to accommodate the users, another user will be assigned in the other beamformer, but with the same subband. This one is actually the main reason why the interference is happening. In the real life, this will introduce the interference and evaluate the performance. If the result is not satisfied, we will reiterate these steps again. So this is the resource allocation. I will try to mention it. This is the figure from the paper. Let's consider the hotspot scenario here. As we can see here, there are 9 users in this sector. And then let's suppose we have n number, that is 3 number of beamformer and 4 number of subband. Because there are 9 number of user, we will assign 1 user in 1 beamformer and 1 subband. So 1, 2, 3, 4. Because we did not have the correct number of subband, another user will be assigned in the other beamformer. So 5, 6, 7, 8, and 9. And this one, we can see here, the user 1, 5, and 9 is assigned to the same subband, but different beamformer. This case is the case when the interference of the main lobe will be happening. So the main lobe interference usually happen when the number of UE is more than the available subband. This is the illustration of the interference in the same main lobe. The star symbol is the user 1, and this is the user 5 and user 9. As we can see here, all of the 3 user is located in the same subband, but different beamformer. But because of that, when the 3 users is served, the 3 of them will suffer from the main lobe interference. So about the evaluation, how did this problem is solved? So the author compared the proposed algorithm with another algorithm. So we just randomly allocate the users to the subband and beamformer, and also the genetic algorithm, which I will not explain it in this presentation. And the following is the result from the proposed interference algorithm. avoidance algorithm. Sorry. So the proposed algorithm get the higher throughput in this evaluation, and as we can see here, this is the 3 different measurement of the beam width. With this smallest beam width, we can see that we can achieve the higher throughput here. But with the higher beam width, the throughput will be lower, because with the higher beam width, there is more chance to get the interference. And the proposed algorithm get better performance compared to the 2 others algorithm. And then the number of iteration to the algorithm to get the desired level of surface is less than the other 2 algorithm, and it has a stagnant or consistent number of iteration regardless of the number of users. So in conclusion, the proposed algorithm, the main lobe interference, achieve higher throughput, and the MI algorithm achieve the level of surface with less iteration. Sorry, this one should be surfaces. And this one is the main point. So the inter-user interference in main lobe usually happen when there is more users in one sector than the available subband to be allocated. And then I will briefly mention the other issues and challenge for the millimeter wave. The one is blockage, as we already know, because of the high path loss. A small blockage will hinder the transmissions, and also the user mobility. So the user mobility issues is actually when we synchronize the transmitting and receiving beam with high user mobility could be a challenge, because the user is moving and need to be constantly adjusting their beam, both for the transmitting and receiving beam. And also due to the small cell size, an offer between base stations should be handled intelligently and quickly, because the user is moving quite fast with the small base station coverage cell size. I think that's from me. Is there any question? I hope you get my point or my idea. Thank you.
Thank you. Similarly, I hope you can try to refer to the term they used before. For example, they use PRB, they use layers. So maybe you can try to adjust. And you can also try to think about in the first paper, there are several algorithms. So you can check with Dennis whether this algorithm can be replaced in the max scheduler. And if you can replace it, how you can do it. So I hope 3 of you need to work in a single team, as a single team. Dennis need to explore everything about the scheduler. He need to show you where is the scheduler, how do you do it, and based on the knowledge he shared to you, Jojo need to think about how to extend the existing scheduler to support MIMO. And Ecomoc, you can also think about how do you implement the algorithm to existing scheduler. Then to the end, we can have a different kind of scheduling algorithm. Then we can decide to use which one for different service. Okay?
Okay,
Do you catch my idea?
Oh, okay.
You need to work together as a team, study together as a team. Then you can discuss with the others. That's quite important. Don't do the job by yourself. You need to study the background knowledge. You need to discuss with the others. you need to exchange the idea with the others. For example, in Jojo's talk, he mentioned about CQI. So he need to know where can you get the CQI. If you want to adjust the pre-coding matrix, how can you do it? You need to think about you already have the source code at hand. How can you enhance it? So the background knowledge is just used for you to understand some common terms. You need to implement the idea in OSC source code. That's our goal. So please tightly co-work so you can share the knowledge with the others. Then you can learn fast and solid. Okay, thank you. Very good. So Dennis, please try to discuss